Alright, unfortunately, due to the bad weather that we have back there, we're not able to have a class today. So I decided to record the content, the final content regarding the Z-transform in my office, and hopefully you will benefit from them because you will be responsible from these concepts in the final. So whatever I will upload, including this one and the future ones, you will have to carefully watch and study from the book as well. So I will have to continue with the Z-transform, and as you may remember, we were covering the properties of the Z-transform. The last property that we saw was this seventh property regarding the convolution. And after that, we have seen a few examples. In this important example regarding the system transfer function, we have seen or we have used several properties. For example, we use the linearity property because, as you see, we are combining shifted versions of y and x. So we had to combine them. That's where we use the linearity, and we use the time shift property. N minus 2 corresponds to what in Z domain? And finally, we use the convolution versus multiplication property by saying that if y of n is equal to h of n convolution x of n, then we must have y of z equals h of z times x of z, which immediately defines as h of z equals y of z divided by x of z. That's what we called the transfer function. And from the z domain we obtained a polynomial division. The classical way to solve this problem is to split the polynomial division into first order polynomial portions and then invert them using our tables and knowledges. Another example that we can construct is a first order difference. So let's write the name, first order difference. This first order difference example defines the impulse response of our discrete time system h of n as delta n minus delta n minus 1. Now what does it make when you convolve any signal with this h of n? First of all, let's see that y of n is equal to x of n convolution h of n, which is equal to x of n convolution in parentheses delta n minus delta n minus 1, and that would make xn convolution delta n first, and a convolution with an impulse is itself, so that will make x of n minus xn convolution delta n minus 1, which will shift our signal to the right by 1. So we have to subtract xn minus 1. So the convolution result is this. So what is that? It is the signal minus its shifted version. What is the difference between the signal and its shifted version? This is what we call the first difference. A first difference is a nice operator which depicts some sharp transitions. For instance, if your signal is like this, a unit step function, sort of, or if you think of it as a profile of an image, then that would correspond to an edge transition from dark levels to bright levels with these labels -1, -2, etc. over the axis of n. So this is xn, and let's draw now xn minus 1. That would be one shifted version of the top signal. Of course, these are continuing to the right and to the left. They are infinite extent signals. So when you subtract the second signal, so let's make a subtraction operation like this. 1 minus 1 will give you 0. The others will all give you zeros, and 1 minus 1 will give you 0. The last 1 minus 1 will give you 0 at the position of 1. And at the position of 0, it will be, the result will be 1 minus 0, which will be a 1 only at this point. The others are 0 minus 0, which are all zeros towards left. So as you see, we have zeros towards the left and towards the right. So what did we get? We get the edge point. In fact, if you closely inspect the edge detectors from some well-known image processing tools, this sort of a thing is what they do. They take a first order difference of the signal. But now we are more interested in what the Z transform of this thing is and what's the characteristics of that. So let's come back to Hn equals delta n minus delta n minus 1 thing, and from here we can say that h of z is clearly the Z transform of delta n is 1, and this is one shifted version of it, which will make e to the sorry, it's the Z transform we're talking about. It's not e to the, it's the Z inverse, z to the minus 1 times 1. So 1 minus Z inverse is the Z transform, and from there we can write that y of z is equal to h of z times x of z from the convolution versus multiplication property, and this thing is therefore 1 minus z inverse times x of z. Now in this case, since we are dealing with the Z transform, we have to be talking a little bit about the new poles and zeros. This new thing has a pole at z is equal to 0, as you see, because 1 over 0 will become infinity there. So that's a singularity point. And it becomes identical to 1 when z is equal to 1. So at z is equal to 1, we insert a 0. So the first difference will insert a 0 at z is equal to 1, which may cancel with a pole of x of z, because we are multiplying this expression with x of z. So the region of convergence includes the previous region of convergence, we have to say. And if a pole at z is equal to 1 is cancelled, then the region of convergence may be even larger than that for the first order difference. Now, as the final example regarding these concepts, we can talk about the integration, the opposite operation, which is, for the discrete case, an accumulation. It's not like the continuous integration or finding the area. We are just accumulating term by term. Now, the output of an accumulator, let's call it W of n, is equal to an index k from minus infinity up to the point of time, which is n, of x of k. And we know that that could be achieved by u of n convolution x of n. When you convolve a signal with u of n, then what you do is you accumulate and you integrate. The same formula is valid for continuous time too. If you are integrating from minus infinity to t of x of tau, d tau, that is equivalent to convolving x of t with u of t. So u convolution x will give you the integral, And this accumulator formula is from the previous example, the inverse of 1 minus z inverse. And the inverse of 1 minus z inverse is 1 over 1 minus z inverse, of course. So we can say W of z is equal to 1 over 1 minus z inverse x of z. We can write it like this. And the poles and the zeros of this operation are just the opposite of the other ones. Because it inserts a 0 at z is equal to 0, not a pole, unlike the previous example, and it inserts a pole at z is equal to 1. So we have to say the region of convergence is equal to the intersection of a unit circle, which is the out of a circle with radius 1. This is the unit circle, intersection with the previous region of convergence, whichever is smaller, the region of convergence will be that. And therefore it is sort of reducing or restricting the region of convergence by integration. And normally, since there is a pole at 1, it disables the stability of the system. So an accumulator is an unstable system, because this filter with an impulse response of u of n is something unstable. It is accumulating and it inserts a pole at 1, and that doesn't include the unit circle. Remember that if you don't include the unit circle, then you're not stable. So this is something unstable, and this portion here would correspond to u of z. That is the z transform of u of n. In fact, you can find it with direct calculation. What is u of n? It is 1 to the power n. Let's write it. U of n is equal to 1 to the power n u of n. And from there, u of z is automatically 1 over 1 minus 1 times z inverse, which is 1 over 1 minus z inverse. That's how you can also interpret the z transform of the unit step function. Alright, so these are the examples of a differentiator and an integrator. An integrator will make it unstable, quite unstable. Now, I will continue with a new property, and that property is the 8th property, differentiation in time. Sorry, it's not in time this time, it's not differencing in time, it's differentiation in z domain. In z domain. So we can think of it like this. We are applying some sort of a duality formula. It's not this time a differentiation in time. This formula is a little bit more complicated than the continuous time case, because we know that in the continuous time case, if you differentiate a time signal, what you get will be j omega times the Fourier transform as the Fourier transform. Or if you differentiate in the Fourier transform with respect to omega, you will get t times, minus t times x of t sort of thing. But this one will be a bit different from that, because the frequency content is in the exponent e to the j omega. Therefore, the z is equal to e to the j omega. The differentiation of z is quite different from the differentiation of omega, which is originally in the exponent. The formula that we get, nevertheless, you can do it, and you can still prove this. It's not very magical. Will give us this kind of an equation. If you differentiate, if you take the derivative of x of z with respect to z, and then later multiply it with a minus z, that would correspond to the time domain, discrete time, in discrete time, signal n times x of n. Quite strange, but it's doable. So this is your new Z transform. And if you closely inspect what may happen in the region of convergence, think of it as a polynomial rational. In the denominators, the denominator polynomial will give you the poles, right? And when you take the derivative of that, the denominator will be squared. But the positions of the poles will not change. It is still the same poles, but this time we will have multiple poles of those points. So the region of convergence doesn't change. We are inserting a 0 at z is equal to 0 here, but that wouldn't make anything because z is equal to 0 is out of the plane. It's a singularity point. So the poles won't change. The positions of the poles will not change. And we have to say region of convergence stays the same after this kind of an operation. Now, how can we use it? Well, maybe the most significant example regarding the utilization of this property was our previous example that we solved using the Taylor expansion, which was like this. What is the inverse Z transform of this? A Z inverse. You remember this, right? And the region of convergence is given as the radius greater than absolute value A. Previously we solved it using the Taylor expansion of this, and we obtained a long infinite extent polynomial, and the coefficients of those polynomial Z inverses will correspond to the time samples. But now we are going to apply this awkward looking formula to see that minus Z times the derivative of this Z transform is n times x of n, but the derivative of a logarithm will give us something quite nice, which is a Z inverse, that is the inside of the logarithm, divided by 1 plus a Z inverse, and the derivative will still have the same region of convergence. Okay, now let's proceed from there. We can say that we can find at least the inverse Z transform of this kind of a thing, because that's a polynomial. In fact, this polynomial, the inverse Z transform of this polynomial is, there's an A multiplication, so let's keep that A here. Since it should be minus AZ inverse in the denominator, that means we are having minus A to the power n, without thinking this, we are excluding the Z inverse for the time being. Then we are going to apply a shift to this whole thing. U of n is the one without Z inverse, and from here we will have A times minus A to the n minus 1 U of n minus 1, which will be with Z inverse. Okay, so the inverse Z transform of this thing is here, and that is equal to this new expression. And the inverse Z transform of that would correspond to n times x of n from the formula. And n times x of n is A times minus A to the power n minus 1 U of n minus 1. Alright. That would make x of n equals 1 over n, or yeah, I forgot the minus sign here. There's a minus Z expression over there as well, so I have to negate it again, because I took the I took the derivative of this thing, and then we didn't take the negative of that. So we need a negative here. Let me put it on the left hand side of the equation, and then we will have minus 1 over n. And a times minus a to the power n minus 1. Excuse me, it's not from this minus sign. I'm sorry about this. Let me correct it. This is the whole correct equation, and we have 1 over n times minus a to the power n minus 1 u of n minus 1. Okay, this is the correct formula without any negatives. It must have been already incorporated. The negative sign in my notes comes from this. A to the n minus 1 times a is a to the n. So we can write it like this: 1 over n times minus a to the power n. But the signs of minus a to the power n minus 1 and the signs of minus a to the power n are just the opposites of each other. They are the negatives of each other. That's why we need to put an extra minus sign just to make sure that this a goes into the parentheses to make it minus a to the power n u of n minus 1. Alright, that is the final expression. And in this expression you can compare it with the previous one if you wish. Just go to those notes in the video. I'm not sure if I did it here. Let me scroll up. No, I must have done it in a previous page. Not this one. Yeah, there it is. There it is. Look at that. Minus 1 to the power n plus 1 a to the n over n. Isn't this equal to minus 1 over n minus a to the power n u of n minus 1? They are the same. This minus to the power n is taken out as minus 1 to the power n plus 1 with a minus sign, because their signs are just interchanged with the previous one. So this equation is precisely the same as our new result. Let's go. Yeah, there it is. I'm sorry. So we could solve the same problem using this differentiation in z-domain property. Usually differentiation in z-domain would be helpful if you have some logarithm expressions like this, because their derivatives are quite simple. They extract the inside polynomials of the logarithms in the denominator, and therefore they become manageable. So this is an alternative way to think of it. Now the new property, the ninth property, is also known as the initial value theorem. And these initial value theorems are a little bit easier than the initial and final value theorems of the Laplace transform. Of course, the initial value theorem is valid only for causal signals or systems. If x of n is equal to 0 for n less than 0, in other words, it is initially at rest and then it exhibits itself, then we can find the initial value, which is x of 0, of the signal using this formula, as z goes to infinity x of z. So it's a limit. It looks like magic, but it's terribly simple. Just think of it like this: x of n, x of z it was this, right? X of z is equal to, since it is the signal is 0 for m less than 0, it is a plus b z inverse plus c z to the minus 2 plus d z to the minus 3 plus e z to the minus 4 plus etc. Now this is x of 0, a, b is x of 1, c is x of 2, etc. We know it. And look what happens when you take z goes to infinity. As z goes to infinity, we have this one, z to the minus 1 to go to 0. Z to the minus 2 goes to 0. Z to the minus 3, z to the minus 4. All of them goes to 0. And then we are left only with a, which is x of 0. That's why x of 0 is limit as z goes to infinity x of z. There's nothing fancy about it. Of course, it looks very easy if you write it in the formal linear polynomial form. But if you write it in a form like 1 over 1 minus a z inverse kind of thing, then it would mean something. Because as you see, as z goes to infinity, a z inverse goes to 0, and you are left with 1 over 1, which is equal to 1. So that would be what x of 0 is. You would immediately say it from there. Or if it's a more complicated polynomial rational, or if it is in the form of a logarithm, as we did in the previous example, then this limit may help you to extract the particular information of x of 0, which is equal to limit z goes to infinity x of z. So that would be the initial value theorem. These properties, the initial value theorems, etc., we all know that, as you may expect. They are in the book, tabulated in the book. Sorry about this last example. It was out of the recording limits. So let me put it in the recording limits. The last example was this. It is indicating that the polynomial division, like this, a polynomial ratio or a logarithm, etc., they are more suitable for applying this initial value theorem. Because otherwise, if it's in the form of this linear polynomial, then there's nothing fancy about it. Of course, a is the initial value. For the others, it would be meaningful. So, about these tables, or the tables of properties, they are in the book. So, please bring those tables, take a copy of those tables, and bring them to the final. In the final, you will be bringing the original crib sheet, which you can find in this Facebook page, and all the tables from everywhere, including the Fourier transform, discrete time, continuous time, the Laplace transform, Z transform, etc. Okay. Now, how much time do we have? We still have some time. Okay. Let's continue with some further examples regarding the linear and time invariant systems. We have already seen an example about the linear and time invariant system. In fact, even the first order difference, the first difference itself was a linear and time invariant system. But let's complicate things a little bit more, and then try to see if we can still achieve a solution for these kind of things. So h of z could be given as like this: z cubed minus 2z to the 2z square plus z divided by z square plus 1 over 4 z plus 1 over, what is that, 1 over 8 probably. Hopefully, because in my notes, since my handwriting is very bad, I just cannot read it. Let's say 1 over 8. Now, we have to make some inspections from here first. You have to give me the answers of these questions. Interesting questions. Is the system causal? Now, what kind of a question is that? I'm not asking whether the system is or the impulse response is right-hand sided or not. It could be right-hand sided, but if the right-hand sided signal starts from somewhere at the negative indices, then we cannot say that the system is causal. For example, u of n plus 1 is a right-hand sided signal, but it's not causal because it starts from -1 and goes to plus infinity. So that -1 thing spoils the causality. So the question is different, as you see. Is it causal? And interestingly, this system cannot be causal. It is definitely uncausal, non-causal, or because z cube, which is the power of the numerator, is more than the power of the maximum power in the denominator, which is z square. So z cube is more than z square, which means that when you make a division, you will be left with some z will be left. Will be left. And if there is a z, what does its coefficient correspond to? Its coefficient will correspond to x of -1. Because z inverse's coefficient will be x1, z minus 2, z to the -2's coefficient will be x of 2, the coefficient with itself will correspond to x of 0, but the coefficient of z will correspond to x of -1. So there is at least x of -1, so we say non-causal. As simple as that. Interesting, isn't it? You just take a look at the polynomial division and see that if the power of the numerator is more than the power of the denominator, then it cannot be causal. Now, that was a side question. Let's try to find the inverse, or try to find it. Let's think of the stability or the impulse response and all those things. The inversion could be made by splitting this into first order systems, and I did it already. It's in my notes. I'm sorry about these shortcuts, but this is what it is. There's a 1 over 1 minus 1 over 2z inverse plus 1 over 1 minus 2z inverse. These two will be it. And now I will have to assume something. What is the region of convergence? The region of convergence is z greater than 2, which is a pole of the second term here. So I'm looking for the right-hand sided solution. That would be unstable, by the way. And I don't know if that would correspond to this example. Let's think of it as a separate example, because otherwise I will have to check whether the previous question really expands like this. Probably it doesn't. It shouldn't be. This must be a different example, because we must have the numerator order to be higher than the denominator, and it doesn't happen like this here. Okay, so let's think of it as an isolated individual question by itself, which will give us an unstable system with z greater than 2, and h of n will be equal to 1 over 2 to the power n u of n. That's quite simple, plus 2 to the power n u of n. So stability kind of a question is what we have here, and it's quite obviously an increasing exponential in the second term, which spoils the stability. Alright, and we say that since it's unstable, or let me write it like this, there are a lot of equivalent terms. Unit circle is not included in region of convergence is equivalent to saying unstable, and that is also equivalent to saying the Fourier transform doesn't exist. So these three things could be asked interchangeably. If we're talking about a system, I will say, is it stable or unstable? And you have to check if the unit circle is included in the region of convergence with respect to the poles. If it is included, then you say it is stable. Or if it's not a system, if it's just a signal we're talking about, I can ask you whether the Fourier transform exists or not, and then the answer is the same. You look at whether the region of convergence includes the unit circle or not. If it is included, then you say the Fourier transform exists. Otherwise, you say the Fourier transform doesn't exist. For the stability and the Fourier transform existence case, if they exist, you can safely make this substitution. Z is equal to e to the j omega, and then apply all the known formulas from the Fourier theory that you may have, because it means R is equal to 1 is in region of convergence. Okay. Now we should have started the linear system equation examples, but we just couldn't dive into it. So let's for the first part think of the causality and stability. Stability is simple. Region of convergence must include the unit circle. Causality or non-causal signals or systems means if there are some z terms, then it becomes non-causal, because the coefficient of z will correspond to x of -1. Or you can think of it like this. Look at it. H of z, so that is the causality. If h of z, or limit z goes to infinity, h of z is infinity, if h of z also goes to infinity, then it means the numerator coefficient is more than the denominator. Then you say that it is non-causal. You can also make this kind of a check for causality for discrete time systems, of course. Now the example discrete time systems we will continue next hour, because it may be a good time to stop this video. Afterwards I will continue with a new video, so I'm gonna stop